This one. Hello, everyone. Thank you. Yes, I'm coming from Labs, which is a company behind the creators of the ZK Sync protocol. Obviously, we're building things on ZK for a very long time. We built the very first ZK rollup on Ethereum. And I want to give you an intuition why ZK is the end game, like why it's such a transformational technology. I'll start by saying that, just reminding you that Ethereum is very young age. It's going to get 9 years old this year. And Ethereum is the representation of the Web3, this new generation of the internet. And if you remember, or maybe you can like imagine how the Web 1 looked like when it was 9 years old, it was quite unsafe, it was very inconvenient, and it was very slow. And this probably sounds familiar to how things are currently in our world in crypto. And all of that gradually improved. We got faster modems, we got better browsers, better JavaScript frameworks, people started building more usable applications. But there was one thing that kind of enabled the internet as we know it today. It was very important. It was like a small change, a small like specific protocol that kind of like made a tectonic shift, like a paradigm change from what was possible, what was not possible in the web. And to explain it, we have to remember that the internet cannot run on a single server. It's a connection of many networks run by different parties. You can be in Dubai connecting to the server in New York, routed through Europe. You don't know who operates all those servers, right? If you want to connect to your bank or to some medical database or your work database with some sensitive data, you need the integrity of communication. You need to make sure that no one in between can mess with your connection, read your data, but more importantly, write data on your behalf and like transfer all of your money somewhere or like use your credit card, which you're going to put on your web shop. And to achieve that, you needed a cryptographic protocol, and it came with HTTPS. It was not there on day one. The early web, like in early 2000s, many websites were not HTTPS protected. And it was dangerous for this reason, right? And HTTPS, TLS, SSL revolutionized the web. And while the Web3 today is also quite unsafe, inconvenient, and slow, and all of that is improving, we need something similar. Because the web cannot run on a single, just like the internet cannot run on a single server, the internet of value, for fundamental reasons, cannot run on a single monolithic blockchain. I hope that we all agree on this. Like, it's just technologically not feasible, but also socially not feasible to have like one single all-sides-fits-all solution for all communities, all businesses to just agree on, okay, we're going to be building on this one single configuration blockchain. So there must be multiple blockchains, like a multi-chain world, but it must be seamlessly connected, just like the internet is connected, without having to worry, without having any additional trust assumptions about all these people in between. Like, this is not how the world of multi-chain works today. If you want to connect from like Ethereum to Solana and send some messages or send some value, you rely on trusted bridges, also known as multisigs. So you just rely on some people relaying the trust for you. And maybe you kind of like, you take two blockchains and you trust the people who run the bridge in between. You cannot really extend this trust like to the next hop, like to multiple like bridges connecting multiple chains. And the future is where we have like hundreds or thousands of permissionless chains that needs to be operated all in parallel and all be connected. And so we need something that will enable this world where the users don't have to think about where they are, don't have to think about bridging in the first place. All they do is like they have their account with wallet on, like they have some assets on chain A, because you cannot, like you think of chains as cities. You can only physically be present like at one point of a time in one city, or your car can be in one city. You can move it over bridges or roads to other places, but like at any given point of time, it's in one place. Same with value. Your value can be only on one chain, right? So once you have it, like let's say like on like rollup A on Ethereum, what you want to do is you want to interact with a dApp on some other chain. You should be able to do it in just one click, right? Like confirm in your wallet, and it goes, transaction goes there, does something atomically, and comes back with a result. And to get there, we need trust-free interop at arbitrary scale. Just like the internet, you don't think like, oh, internet can only run on 1,000 servers. No, you can add more servers, more data links. You can expand it indefinitely without losing this seamless connectivity, because HTTPS solves it for you, right? Like no matter how many hops or connections are, like servers are between, you always operate end-to-end encrypted and end-to-end authenticated. And we need the same thing here. And the naive approach is, as I said, like just don't scale trust. They can scale something, but not really trust. And we need a transformative invention. And here the zero-knowledge proofs come to the scene. Because zero-knowledge proofs, how many of you are familiar with zero-knowledge proofs? Okay, great. So you probably know about the privacy aspect of it, and you know about the succinct proofs of computational integrity. Computational integrity is a much more important property of the proofs. We basically compress computation. We can perform a very large array of operations, produce a proof, and then anyone can verify it in less than 1 second from a mobile phone. And this way you you do a very small computation, but you verify a very large result. And this enables, like if EVM is HTTP of the blockchains, then ZK is the HTTPS of the blockchains. Because in the world of blockchains, you need to scale trust in computation. Like what blockchains do, those are like decentralized databases. Decentralized authenticated databases that operate on like a large state computationally, and then anyone can verify them. It's verifiable computation, right? So with ZK, you extend this trust like indefinitely to as many chains as you need. And if you want, like I also want to give you an intuition how this works, just like internally, why it's possible. Through recursion. How many of you are familiar with recursion? Great. So let's start with a simple transaction on a ZK rollup. We can produce a proof, like the transaction can be large, it can be doing some like complex things, but then we can produce a short proof of verifying the operations, all of the logic of this transaction, including signature, like sender balance, recipient balance correctly updated, all the logic of smart contracts executed, etc. We have this one single proof. Then we can take proofs of all of these transactions and generate a proof that verifies multiple proofs together, which is quite a simple thing, because verifying the proof is also computation. Then you can repeat this process. Then you can take the proofs of proofs and generate a proof of them. And you can repeat it more until you get the single proof of a block. And then you can repeat it further until for multiple blocks, until you combine it into a single succinct proof that verifies all of the blocks of all the rollups that settle on Ethereum. What you can do next is you can verify the Ethereum execution itself, Ethereum's block. And you produce a single proof which you can verify from a mobile phone. And voila, we turn all of the mobile smartphones in the world in Ethereum full nodes. Like you have 1 billion, not light clients, actual full nodes that verify every single transaction on Ethereum from Genesis and on all of the rollups, ZK rollups, that settle on Ethereum. And they can all trust each other because they don't trust people. They trust math and code. And yes, if you have a error in the protocol or in the code, of course, it's going to be a problem. So you want to go follow security practices. But like as long as the code and the protocol is safe, it's like bulletproof. It's just math. It doesn't matter what incentives people have, who is compromised, who is not compromised, how the keys are managed. All of that does not matter. You trust pure math. which is very, very powerful. And this is what I call ZK singularity, a single ZK proof that verifies everything from your phone in 1 second. And this is happening this year, and it's time to build on ZK. Thank you. Do we have time for questions?
Do we have any questions? Do we have any questions? If you can just raise your hand.
Yeah, thanks for the presentation. I'm just curious. So I think one of the challenges that ZK rollups are facing today, or you can tell me if it's a challenge at all or not, is the gap between producing the rollup block and actually producing a proof, which is why many of rollups, they actually bundling many blocks into a single proofs, but from user's perspective, as your example with mobile phone, it actually might look like, well, first they send transaction, but then they need to wait for some time between this, or when this transaction will actually be verified, when there is a proof actually put on Ethereum. We also need to take into account that Ethereum finality is slow, and also maybe to reduce this gap, we need to add more hardware to compute this faster, but then it actually gets very expensive to generate these proofs. I don't know how ZK Sync team is solving these challenges, basically reducing the gap and reducing the cost of producing a proof. Yeah, thank you.
Those are great questions. So let's start with latency. The latency is today some minutes to generate the proof. It's going down to seconds. Like we have the new generation of the protocols and better hardware. The proofs, like from the moment you submit your transaction to the moment you have a proof of some checkpoint of some block to this transaction, by the end of this year, it's going to be like 15 seconds. Right, so like and then from there, so there are teams working on a hardware acceleration, like what they call VPUs, verifiable processing units, specifically for cryptography, also like general purpose, like GPUs for graphic, you have VPUs for cryptography. It will bring it down to like basically close, like let's say 2 years from now, it's going to be real time. ZK is going real time, like synchronously with generating transactions, you will be generating kind of like almost like with a lag of like 1-2 seconds, you will be generating proofs. Now, but like even if you have to wait 1 minute, this is nothing than comparing to optimistic rollups where you have to wait 7 days for objective verifiable finality on layer 1. So that's with regard to latency. With regard to like you have to wait for Ethereum finality, today the finality of Ethereum blocks is roughly 10 minutes. This is going to change and we're getting to single slot finality, so it's going to be like something like 12 seconds. But like how is it different from any other transaction on Ethereum? You know, if you send any transfer, any like interaction with smart contract on Ethereum, you are subject to the same finality limitations. So it has nothing to do with ZK. Like ZK does not kind of affect it in any way. Like optimistic ZK rollups all have the same problem because we all depend on Ethereum. So like with single slot finality with 12 seconds, it's probably going to be sufficient because what's going to happen is the L2s, like ZK Sync, for example, is working actively on decentralizing the sequencer. We already have a test net with a decentralized sequencer running on hot stuff consensus with less than 1 second blocks. So from a user perspective, when you submit a transaction, you will get in like close to instant confirmation, like in less than 1 second, that transaction is going to be included in the next block. And it's going to be signed by the majority of the stake, or like the quorum of the stake of this decentralized sequencer. So they cannot really revert it without being slashed. It doesn't matter what happens on Ethereum, they already promised to you that it's going to be included. So most likely, if your transaction is like on a small scale, like up to $1 million, it's probably sufficient for you to know that the slashing is going to be much higher if they revert this. And remember, they can never do anything invalid. They cannot mess with the state. They can only like revert, like reorg the blockchain, right? Worst case is a reorg, just like on Ethereum. So your anti-reorg guarantee is backed by the stake. But if it's like really large, if you want to send like $1 billion, then you probably want to wait 12 seconds for Ethereum to confirm, right? So like it's your subjective decision on how long you want to wait for finality. Now coming to the hardware and the costs of hardware. It does not matter how much hardware you need to add, because you only add hardware. You throw hardware at the computation if there is something to compute. So you only need a lot of, like, if you have like 100 or 1,000 times more transactions, sure, you need 1,000 times more hardware, but that's logical. Just like if you scale any cloud computation, if you have like 1,000 times more users, you need 1,000 times more processing power, but those users will be paying for it. For all what matters is the cost per transaction, not the total cost, right? Like, and the cost per transaction is small. Like, look at L2 fees is a bad source. It's not very reliable, but if you go to Grow the Pie or to guessfees.io, they have a really nice visual comparison of the costs of rollups. ZK Sync is like one of the cheapest rollups. Like we're like slightly more expensive than Arbitrum, slightly less expensive than Optimism and Base, with like 1 or 2 cents per transaction on average. Right? And so this is already this takes the on-chain component into the account plus the computation. You have to pay for computation there. The computation is very cheap, and it's getting like by the end of this year it's going down 10x, and with VPUs it's going down another 10x. And it's going to be, I mean, it's never going to be negligible because your marginal cost is always important. Like going from 0.1 to 0.01 to 0.001 makes a huge difference for financial applications, for DeFi, for high frequency trading, because they can do like more trading and like lower margins. And bots can always exploit any additional reduction in the order of magnitude of the costs, but it's going to be like negligible compared to the cost of data availability on rollups. So like definitely better than optimistic rollups because we can do better compression. ZK Sync and Starknet are the only two rollups that do this. We use the state delta approach to publishing the state diffs. So basically we don't publish every single transaction on Ethereum through Ethereum Data Availability Network. We publish the outputs of the transaction. Only like what changed after each block, which storage slots changed. And so it enables us to make the footprint, like the cost of data availability is like 50% cheaper than optimistic rollups. And you could see it in the cost benchmarks before EAP 4844, like very visibly. We were cheaper by 50% than any optimistic rollup. Cheaper than Arbitrum, cheaper than Optimism, like all of them. Now with EAP 4844, because of this like 1 cent, like less than 1 cent, computation costs, it's hard to see, but it's in there. And when the gas prices on Ethereum will go up, optimistic rollups will be more expensive again. And this is going to happen. More questions?
Anyone else? Yeah.
Thank you for your talk. So you sort of pull the analogy of ZK as an equivalent of HTTPS, but HTTPS is like a bidirectional thing in which two entities would create a connection, and from their perspective, what they are doing is sort of symmetric. But for the ZK singularity thing that you later described, it's not symmetric, as in there is asymmetric nature of data source or data availability, so that the prover has all of the data and the verifier verifies the last step. But the verifier may not be able to generate all the data and do all of the intermediate steps should they require it. So my question is, isn't there going to be multiple layers of trust on data sources as well? And what is your comment on the bidirectionality vis-a-vis your analogy to HTTPS?
This is a great question. So this is a rough analogy because obviously those are very different protocols. They operate in a different way. You could also argue that HTTPS can be asymmetric. If I just browse a website with HTTPS, I download the data from this website, but I don't upload anything, right? And it can actually be like in the protocol itself. Like you start with asymmetric key, where you here's a better analogy. Like the website has a certificate of authenticity, which I can verify through the root of the certificate chain, but the user does not have and does not need one, because the website does not need to authenticate this user unless the user becomes a user, like gets an account and so on, right? So also in HTTPS it can be asymmetric, and and it's a good thing. You can communicate, like let's say like you have two different users or two different blockchains. The message can be like one directional, unidirectional from chain A to chain B. You can reciprocate and send a message from chain B to chain A, but you should not need to know all of the data of chain B if you operate the chain A and vice versa. And a good example of the use case where you actually want this asymmetry is banking chains or enterprise chains. So we're in conversations with a lot of financial institutions, banks, like trading companies, like big financial providers. What they want is they want interoperability, but they don't want to disclose privacy of their own users. So they actually want this property. They want to be able to prove that something that affects you happened correctly, but not disclose anything that happens to the other people. And honestly, you also don't want to know, not because, like, you know, irrespective of privacy aspects, you should not need to maintain the state of everyone else. Like, imagine that like the monolithic thesis is right, and like everything can be done on a single chain. Let's say, I don't know, like Solana or something, like, you know. That means that you as a full node operator need to maintain the state of all the applications that run on this chain. All of the games, all of the meme coins, all of the whatever applications that people are building there. And the more people build, like we have 10 billion people in the world, we have millions of institutions, millions of developers building stuff. All of a sudden you have to maintain all of that. You have to verify all of that, like put throughput of data for all of this transaction. Why do you care about them? You should not. You should only care, like, is my data correct? Like, is my account, like, can I verify that whatever new next block was produced did not affect my account in any negative way, right? And that's what zero knowledge proofs enabled. Like, you only care about the state that you care about and ignore everything else. And this is a beautiful thing. I mean, this is not like, this is a fundamental enabler of this internet of value. Otherwise, it's just invisible. Like, everyone cannot verify everyone else's data and state and computation. Tanya.
My question is, so if the operator of the rollup becomes uncooperative, then can the users themselves exit the rollup to layer 1? And if so, what happens to smart contracts that are on L2?
It depends on whether the ZK chain is a rollup or a validium. The difference is how you handle the state of this chain. In both cases, you use your knowledge proofs to verify validity and like block transition and guarantee that the validity is basically secured by Ethereum 100%. Like, nothing can be wrong there, right? In the case of a rollup, the state is published to Ethereum always. So any observer from Ethereum can reconstruct the state. You can run a very simple program which collects, like, picks all the outputs and applies them together, and then you get the new block, the state after the new block, which is an easy, very lightweight operation, unlike optimistic rollups. It's very easy to do. So if the operator becomes uncooperative, and in our case, in ZK Sync, as when we have decentralized sequencer, it means, like, let's say the majority of the stake is compromised, right? And they just stop producing blocks. Fine. Then the rollup, then the users can start putting their requests for transactions on what we call the priority queue. So you can just, like, enforce your transaction from layer 1. And the operators have, the validators of this chain, have to take the transactions from the priority queue and execute them. And if they don't do this, then the chain will enter an emergency mode where anyone can produce blocks on layer 1. And again, they have to take transactions from the priority queue and execute them. Now, and it's always possible on a rollup. You pay to Ethereum, the transactions are more expensive. Every single transaction is more expensive, but they give you this property. It's basically the same security as Ethereum itself. No other protocol can fulfill this, but ZK rollups. Only ZK rollups can have mathematically guaranteed 100% the same security properties as Ethereum. Optimistic rollups cannot do this because you still depend on your ability to submit the fraud proof, and it still can fail, and you know, like whatever. But ZK rollups have the 100% this ability. Now let's consider validiums. In a validium, let's imagine you have a banking chain. You have an account in a bank. The bank operates the data. They store it on their servers. They don't publish it to Ethereum. They still use Ethereum to verify zero-knowledge proofs, and they generate zero-knowledge proofs for each block. So they cannot do anything invalid there, but they can just withhold data for all of the users, and or for you personally, right? So what you can do, you can still use the priority queue to submit your transaction, and everyone else can. And if the bank or whoever the operator of this validium will not observe the priority queue, will not push the transactions from there, then the chain will hold for everyone. And that's your ultimate failure mode. You cannot recover from that, but you can also guarantee that the censorship is not targeted. You cannot target one specific individual user. You can either serve everyone or shut it down for everyone, and in which case all of the state, all of the money in the validium will be frozen, but so will be the stake of the operator. So it's kind of like a self-hostage situation. It's you can blow up the car, but you blow up with the car, right? And rational actors won't do this because they will lose money. Irrational actors, motivated by some other external political motives, could do this. Maybe they are forced by some legislation. So this is a risk factor. If you want to operate on a validium, you have to take into account that this can happen. But this is much better than a sidechain where the operators can just steal money. So they have a lot more incentive. They don't have skin in the game. Here they have skin in the game. But yes, this is slightly less secure, or significantly less secure than a rollup, and hopefully we scale Ethereum completely with ZK rollups, not validiums for some specific. Sometimes you have things that don't require valuable state, maybe oracles. You only want to push them and do computation. So for that, validium works perfectly, or evolution. I think we have one more question.
Yeah, we can take one more.
Yeah, thank you. Great speech. Let's imagine, we have a future, as you mentioned, that every bank has a separate network. Let's imagine one bank has a ZK rollup network, another optimistic rollup, and it's linked, through CCIP, for example, protocol. So how, and I would like to, for example, tokenize my deposit, I transfer it from one bank network to another network. So how do you foresee really, how, first of all, ZK rollups can impact this future, and how you foresee overall, because that's more, let's say, futuristic view, because, if on one side will be the optimistic rollup, on other side the ZK sync, or it could be, for example, ARF recorder for one bank, or Avalanche subnet for other bank networks. So how it will work, let's say, together. So what is really the future in your view?
Very simple answer. Great question. I don't see the future where optimistic rollups exist. In all honesty, everything is going to be, all of them will have to upgrade to ZK or become irrelevant. Because the way, imagine rollups as islands. You have different activity there. So to connect ZK rollups, you can build bridges. Actual highways, think the Palm in Dubai is connected with a bridge. You just take a car and you drive there, right? Now, optimistic rollups can only be connected with ferries, and those will be steamer ferries. Like it's an island where you can only reach like by 7 days sailing to this island. So like to connect it to so sure you will have the ZK rollup ecosystem with like this highway bridges connected, and you will see these far islands of optimistic rollups with like daily sailing steamers going there and back like in 7 days interval, right? Will this coexist? Maybe. I mean, like we'll have like the bustling economy of the ZK rollups and these like far islands.
All right. If you'd like to contact Alex, it's Gluch64 on Twitter.
Yes, or
Nice.
ZK Sync on Twitter.
Or ZK Sync. Yeah, so let's
Thank you.
give him a welcome. Yeah.